Alright, let's talk centripetal force. Okay? So we know how we were looking at the activity with the spinning marble, where you have an object that you're spinning, a marble is spinning in a circle. Just to review, what causes the rotation of the marble? So the marble at any point wants to go which way? This way, but what causes it to turn this way? It's called centripetal force, which we'll label as FC, but centripetal force means a force acting towards the center. So what is that force that's actually acting towards the center? It's actually the walls of the what? The walls of the container, right? So it's the walls of the container. It's an applied force of the walls that are actually moving that marble in a circle. And we talked about if you lift the ring, the ball travels in a straight line. And for A, so how do you explain the rotation? Well, that's because of Newton's second law, F equals ma. There is an applied force, and there is an applied force towards the center due to the walls of the container. And the reason why it wants to travel in a straight line for B is because of Newton's first law, the law of inertia, right? Okay, so centripetal acceleration is this force. Isaac Newton called it a force in which bodies are impelled towards the center. Okay? They want to move towards the center. It's a center seeking force. Okay? So just some questions. So in the video we talked about this. What's the centripetal force that acts on the Earth as it orbits the sun? Yeah, so in this case, the centripetal force is gravity. What about a car turning around a corner? It's not banked. Now, not banked. We will deal with banked curves, but a banked curve is a curve that's on an angle. Okay? So this is not banked, so it's not on an angle. So what's the force, which I'll call FC, centripetal force, that causes a car to turn? What is it? It's the same force that prevented the mass from sliding off the record player. Friction. Okay? I have a link here to something called the wall of death. Well, was it not working? Let's see, the wall of death. It's a good name, eh? The wall of death. So this is the wall of death. Okay, so here's the wall of death. There it is. Alright, so you have a motorcycle going around this wall of death. What do you think is causing the motorcycle to turn in a circle? It's actually the same force that caused the marble to turn in a circle. It's the force, the applied force of the walls of the what in this case? Or whatever, or the wall. Walls of the wall. Okay? Whatever this structure is, okay? You ever been on those rides where they spin you around and you feel like you're glued to the wall? Again, that's the applied force trying to push you towards the center. Because otherwise, what would happen? Which way would this person go? That's actually different. He's not sliding down because of something else. Friction. Okay. Friction would act which way, actually, in this case? Which way? Which way would friction act? This way, up. Now, the thing is, there's a lot of friction here because as you're going around the circle, you saw there's this, okay, I'm going to call it a fictitious force. You saw when things were spinning, they flew off the record player. it almost seems like this is force that's pushing things away from the center, and it's got a name actually. I'll call it, now remember it's a fictitious force. It actually does not exist. It's called the centrifugal force. Alright? And it doesn't exist because what it really is it's just inertia. But the thing is, we can almost think of it like a force. So in other words, if we think of it as a force, we have to imagine that it's pretty strong. And the stronger that force, that frictional force is, what happens to the friction? Sorry, the stronger that frictional force is. Did I say frictional force? The stronger that frictional force appears to be, the friction has to go. Because what's friction? Friction is a function of mu times the what? The normal force. In this case, the normal force will be pointing which way? This way. So if that centrifugal force is bigger, that means the normal force is bigger, which means friction is bigger. Okay? Anyway, so this is the wall. Not that I suggest you try this, but this is the wall of death. Alright. Okay, so again, there is no force that pushes things away from the center of the circle. It's the tendency of the object to want to travel in a straight line. Okay, and we know that's Newton's first law. Here's an interesting question. Why do we weigh less at the equator? It's very small. It's like less than 1%. I can't remember the exact number. But why do we weigh less at the equator? There's actually two reasons for this. Have you ever seen the Earth? Is it a perfect circle? No. It actually bulges where? Where does it bulge? If you were to look at the Earth, okay, this is the equator, and this is the North and South Pole. Which is bigger? Because if it was a perfect circle, it would be the same, right? The diameter as measured north to south versus east to west would be exactly the same. But it's not. Why not? What's the Earth doing? It's spinning. We know that the Earth spins. And as things spin, oops. What happened there? I don't know. It's highlighted. What happens as things spin? They want to push which way? They want to push outwards. So the Earth actually bulges in the center. Because it bulges in the center, that means you're further away from where? The center. And what happens to G? Goes down a little bit. So your weight goes down. There's another reason why your weight goes down too. If you think about it from this point of view, if imagine that you're on the equator, and this is you, and the Earth is rotating, which way do you want to go? You want to travel in a straight line. So it's actually less force actually pushing down on the Earth, because you actually there's this tendency to want to fly off the surface of the Earth. It's very small. Okay, it's a very small tendency. Does anyone know how fast the Earth rotates per hour? It's about 1,000 miles per hour. It's about 1,600 kilometers per hour. So it's actually pretty fast, but we don't really notice it. Okay. Don't worry, you don't have to explain that on a test. I just thought it's an interesting consequence of centripetal acceleration. So let's do some really, really basic questions with centripetal acceleration. Okay, we'll start really, really simple. We'll look at a question like this. You have a mass that's 100 grams attached to a string, and it's being rotated horizontally. So in other words, it's so the string is 1 meter long, and the ball is remember, it's got to be in kilograms, so it's 0.1, sorry. It's 0.1 kilograms, okay? And its speed is 2 meters. Now, this object is rotating in a circle, so it's going like this. if you were to watch it from this, from the side. What's pulling it towards the center of the circle? What's the only force? Right. So, in regards to going this way, the centripetal force is the same as the force of tension. Then the centripetal force is just the force that seeks the center. Now you got to figure out, what is it? Is it tension? Is it gravity? Is it the normal force? Is it friction? In this case, what is it? It's tension, because it's a string, right? So the formula for centripetal force is mv squared over r. The v squared over r is actually the acceleration. So the acceleration is v squared over, this v squared over r. So therefore, the acceleration times the mass is, mass times acceleration is what? What is that? What's mass times acceleration? Force. Okay. So the centripetal force is mv squared over r. And because we know that it's the same as the tension, we could say the tension is mv squared over r. So now we can go ahead and solve this. We have the mass of the ball. We have the speed, which is 2 meters per second squared. And we have the radius, which is 1. So the tension is 4 over 1 times 0.1 is 0.4 newtons. Okay? So that's the centripetal force, which is in this case the tension. Alright, let's do one more question. Instead of rotating it horizontally, we are going to rotate it. By the way, this, I don't know, like at this speed, it probably wouldn't rotate horizontally. It would probably look more like this. Okay? But I ignored gravity in this question. Alright? As you saw with the demonstration, when you rotate something, unless you're rotating at a really high speed, it will look like there should be an angle to it because the gravity is pulling it down. So just for simplicity, I just ignored gravity in this question. Okay. So this could have been like, I could have changed this question to like a merry-go-round, and this could be like a question where you have a child on a merry-go-round and you want to know the force. It's the same formula. So whether it's a merry-go-round or whether it's, is it a merry-go, with the one that goes horizontally? What's that called? Is it a merry-go-round, a playground? Versus the Ferris wheel, which goes vertically, right? Okay. So let's talk about vertical then. All right. So this time we're not going to ignore gravity. We're going to talk about gravity. So we're going to do this. We're going to use the same mass. Okay. We're going to rotate the mass, and it's going to go this way. It's going to go vertically. Okay. Now the question is, what is the minimum speed required to keep the mass spinning in a circle? So yesterday you guys were kind of just guessing what the minimum speed was. I actually kind of just feel it out. But now I'm actually going to show you how you can actually calculate it. It's actually not too hard. Pretty easy. What do you think is meant by minimum speed? What do you think is meant by that? That anything less would cause what? Would cause this to fall, right? The circle would collapse. So if it's minimum speed, it actually implies something. Minimum speed actually implies that there is no tension at the top. The tension at the top is actually 0. Yeah. Okay. So that's what it implies. That when you have something traveling, in this case with minimum speed, that means that the tension at the top is 0, because the only thing acting up here to pull it back towards the center would actually be gravity. That's it. That's what's acting to pull it down. Anywhere else, it would be a combination of gravity and tension. So we pick a point, for example, here. Okay. Well, gravity and tension are going to be working, but up here, with the minimum speed, the only thing acting on the ball is gravity. But what about over here? Let's think about this here, okay? Let's think about this position. Which way is the center? Up. So, which way is gravity? Down. So, should there be tension at this point? It should be. In fact, the tension has to be greater than what? Has to be greater than gravity. That's what's going to happen. It's going to not go towards the center, right? Okay, so this is what we know. We know the radius of the string is the radius of the circle is 1 meter because the string is 1 meter, right? We know the mass is 0.1 kilogram. And we know that at the top, there is no tension. So, if the centripetal force is mv squared over r, at the top, the only force acting is what? Gravity. And we know what the formula for gravity is, don't we? What is it? It's mg. So we can set these two equal to each other and say, okay, well, at the top, mg has to equal mv squared over r. And look what you notice. You notice something. The mass is irrelevant. Totally irrelevant because they cancel out. So we can solve for the speed. We can say, well, okay, well, the speed has to be the square root of g times r. So in this case, it will be the square root of 9.8 times 1. So square root of 9.8, which is what? Can't be 0. What is it? 3.13. Okay, so here's the thing. We know now what the speed of this rotation must be, right? We know it's got to be 3.13 meters per second. What is then the tension at the bottom? We know there's no tension at, so anytime you come across a question like this and it says minimum speed, in this scenario, we know there's no tension on top. Okay? But there has to be tension on the bottom. So let's figure out what that is. Let's change the color. So let's look at the bottom. At the bottom, we know that the speed is 3.13. So tell me if this makes sense. The centripetal force has to be the difference between the tension and the mass. Tell me if that makes sense. Centripetal force has to be the center seeking force, right? Okay. So it has to be the sum of this one plus this one. Well, if it's the sum of these two, well, this one's pointing which way? And this one's pointing. So that center seeking force would have to be the net force between tension and gravity. So we could solve that. We know what the centripetal force is because we know it's defined as what? mv squared over r. And that has to be, so here's my centripetal force, has to be the sum of the tension minus the weight, which is mg. Okay, so let's finish it off over here. So let's rearrange this and say tension has to be the sum of the centripetal force, the net centripetal force plus the mass times the g, or the weight. Okay, so what is that? That will be 0.1 times, we know what the speed is, 3.13 squared over 1 plus 0.1 times 9.8. I'm sorry, I'm really squeezing it in. Okay, let me just put the answer. This is like all over the place. It's like we're writing this in some sort of a hurricane. Okay, so it's mv squared. We already know what v squared is, don't we? It's 9.8. So this is 9.8 times 0.1. That's about 1 over 1. So that's 1 plus about another 1. So is it about 2? What is it exactly? 1.76. Okay. And I always suggest when you get an answer, see if it makes sense. What would happen? Let's think about this for a second. What's the weight of this object? The weight is mg, right? Now, m is 0.1. M is 0.1 and g is 9.8. So the weight is about 1, right? It's about 1 newton. Now, does it make sense that this is bigger than that? What would happen if they were the same? And according to Newton's second law, F equals ma, if they're the same, that means the net force would have to be what? It would be 0. So at this point, if the net force were 0, which way would this move? Good question. It would go this way because of Newton's first law. So it can't be 1. It has to be more than 1. So does this make sense? Yes, it does. All right. That is the end.